Right now, the HiRISE camera aboard NASA's Mars Reconnaissance orbiter is holding images from October 3rd of interstellar object 3I Atlas, images withheld for 6 weeks, capturing the visitor at a resolution of roughly 30 kilometers per pixel from 28 million kilometers away, while 20 distinct anomalies contradict every established model of comets, leaving scientists unsettled. On the surface of Mars, HiRISE resolves features down to 30 centimeters. At the distance to 3I Atlas during the October flyby, that translates to imaging detail finer than anything European probes TGO and Mars Express managed. Yet NASA locked those data away until tomorrow's special briefing on November 19th. The silence was calculated. The mystery is deliberate. Here's the problem. The object flew past Mars 10 times closer than it will approach Earth, offering the sharpest possible glimpse before it vanishes forever into the void. TGO and Mars Express released their data almost immediately, showing fuzzy streaks that revealed nothing. HiRISE saw more, and HiRISE said nothing. 3I Atlas arrived from interstellar space traveling retrograde, moving against the grain of solar system traffic, yet its orbit aligns within 5 degrees of the ecliptic plane, the flat disk where planets circle the Sun. For a random interstellar traveler, the odds of such alignment are roughly 0.2%, 1 in 500. That alone would be curious. But the comet's timing sharpens the unease. It arrived positioned for close passes near Mars, Venus, and Jupiter, a trajectory researchers calculated has a probability between 0.005% and 0.0002% depending on the statistical model applied. 1 in 20,000 at best, 1 in 4 million at worst. Stop and consider that. An object entering from interstellar space, somehow threading a path that brings it within optimal viewing range of multiple planets and major spacecraft. Then there is the anti-tail. Comets develop tails when solar radiation pushes gas and dust away from the Sun, creating the familiar backward plume. 3I Atlas grew a forward-facing jet, a sunward anti-tail that aimed directly into the solar wind. Radiation pressure should push that material away. It did not. The jet persisted through perihelion and beyond, defying the physics that govern every other comet on record. Comets that survive perihelion typically fragment or lose structural coherence. 3I Atlas remained intact, its anti-tail stable, its envelope unbroken. Now about the data. Spectroscopic analysis reveals the object is dominated by carbon dioxide, with water comprising roughly 4% of its composition. Standard comets are water-rich. This one is not. It also carries high concentrations of nickel, minimal iron, and detectable traces of cyanide, a chemical signature that matches no known body in the solar system. The composition suggests interstellar ice formed under conditions profoundly different from anything near the Sun. That would be an adequate explanation, except the polarization measurements fracture it. Polarization describes how light waves align after reflecting off a surface. Every comet observed to date produces predictable polarization patterns based on grain size, composition, and scattering angles. 3I Atlas shows extreme negative polarization, patterns never recorded in any previous comet. The light coming off this object behaves as if the surface materials are fundamentally alien, structured in ways current dust models cannot replicate. Researchers have no analog. They have no explanation. Here's where it gets interesting. Despite outgassing from up to 7 distinct jets, visible in multiple wavelengths, the object exhibits almost no non-gravitational acceleration. When comets release gas, the jets act like tiny thrusters, subtly altering the trajectory. It is measurable. It is predictable. For 3I Atlas, the non-gravitational acceleration parameter A3 registers at 0.0 plus or minus 0.1 times 10 to the negative 9th astronomical units per day cubed, effectively 0. The jets are firing, the trajectory is not changing. That should be impossible. On October 29th, observers noted the object appeared 4 arcseconds off its predicted position, a deviation requiring either unexplained mass loss or unmodeled acceleration. Tiny, yes, but detectable, and inconsistent with a purely gravitational path. Models attempted to account for outgassing thrust, they failed. Models attempted to account for fragmentation and mass shedding. The object did not fragment. Something is pushing or pulling 3I Atlas in ways that do not fit. Think about what that means. An object massing approximately 33 billion tons, 1,000,000 times the mass of Oumuamua, the first confirmed interstellar visitor, is venting material into space without experiencing the recoil physics demands. Either the mass is vastly greater than estimated, anchoring it against jet forces, or the outgassing is not what it appears to be. The brightness tells a stranger story. 3I Atlas has demonstrated erratic spikes and fades with no clear periodicity. It turned noticeably blue after perihelion, a hot blue appearance some researchers compared to exhaust-like activity. Though no propulsion mechanism is proposed, outbursts of pure blue gas suggest fresh ice sublimating in real time. Yet thermal models for ice sublimation do not match the observed heat signatures. Standard comets emit characteristic spectral lines from gas jets and dust. 3I Atlas lacks those signatures. The brightness does not correlate with expected dust or gas emissions. Observers detected water sublimation beginning at 3.5 astronomical units from the Sun, far earlier than typical comets, which generally activate closer to 2 AU. Early activity implies volatile ices with unusually low sublimation thresholds or an internal heat source warming the nucleus ahead of solar heating. Either explanation fits only if the object's interior composition is unlike anything previously catalogued. Rotation remains uncertain. Some data suggest a tumbling motion. Other observations hint at a 16.2-hour spin period inferred from dark lanes that appear and vanish in imaging. Jets remain unsmeared across exposures, implying either slow rotation or a geometry that keeps active vents facing observers, regardless of spin. The shape is inconsistent. Density estimates fluctuate. Metallic reflectivity has been proposed based on polarization quirks, but no consensus exists. Here's where things get strange. A glowing halo surrounds the nucleus, extending roughly 500,000 kilometers. A sphere of diffuse material far larger than conventional comets. Embedded within that halo, a detached ring structure described as a ghost shell spans 1.2 arc-minutes as viewed from Earth. The shell's geometry implies a sudden explosion-like event ejecting material symmetrically outward, yet the nucleus shows no fragmentation. Explosive outbursts have been documented in comets before, but they typically leave debris and alter the object's structure. 3I Atlas expelled a shell and remained whole. 2 fragments, equal in brightness, appeared separated by 12 pixels in high-resolution imaging. Twin fragments are unusual, but not unprecedented. What defies easy explanation is the hexagonal symmetry detected in the jet structures, 84% hexagonal alignment, a geometric precision rarely seen in natural outgassing. Hexagons suggest underlying structural regularity, either in the nucleus's surface topology or in subsurface venting channels. Natural processes can produce such patterns under specific conditions, but the degree of symmetry pushes probability. Read between the lines. NASA withheld HiRISE data for 6 weeks. The European probes released theirs immediately, showing nothing conclusive. HiRISE has the resolution to image structural details at the scale of tens of kilometers. If the object were an ordinary comet, there would be no reason to delay. If the images revealed something unremarkable, they would have been published with the rest. The delay implies something in those images required interpretation, verification, or perhaps careful framing before public release. The coincidence with the wow signal adds another layer. In 1977, the Big Ear radio telescope detected a 72-second narrowband radio signal from the direction of Sagittarius, never repeated, never explained. 3I Atlas's trajectory aligns within 9 degrees of that source direction, a coincidence with roughly 0.6% probability, alone meaningless. Combined with the other anomalies, it forms part of a broader pattern of improbabilities stacking into implausibility. Radio frequency emissions from the object deepen the puzzle. Observations detected absorption features at 1665 to 1667 MHz, the hydroxyl radical lines. Comets typically emit at those frequencies as water molecules break down under ultraviolet light. 3I Atlas absorbs. Absorption implies the object is positioned between the observer and a background radio source, with hydroxyl radicals in the foreground selectively blocking those wavelengths. That geometry is unusual. The behavior is atypical. Then there is the solar correlation. For months leading up to 3I Atlas's perihelion on September 28th, the Sun produced no X-class flares. On October 30th, 2 days after perihelion, a sudden cluster of X-class flares erupted and continued for days. Solar activity follows an 11-year cycle, and the current cycle is ramping toward maximum, so flares are expected. But the timing, quiet for months, then a burst immediately post-perihelion, has prompted speculation about whether the comet's close passage could have triggered magnetic instabilities in the solar corona. Mainstream solar physicists dismiss the idea. The energy scales do not align. A comet, even a massive one, lacks the magnetic field strength to influence the Sun. Yet the correlation persists in the data, unexplained. Stop and consider that 3I Atlas has defied every fragmentation expectation. Comets that pass within 0.4 astronomical units of the Sun, this one reached perihelion at roughly 0.39 AU, experience extreme thermal stress. Surface temperatures exceed 400 Kelvin. Volatile ices boil away. Structural integrity fails. Fragmentation is common. 3I Atlas remained coherent. Its envelope is stable. The nucleus, whatever its true composition, survived conditions that shatter most comets. Estimates place the object between 5 and 20 kilometers wide. At the lower end, it is comparable to large asteroids. At the upper end, it rivals the nuclei of the solar system's great comets. The mass estimate of 33 billion tons assumes a density consistent with porous ice and rock. If the object is denser, if it contains significant metal or compressed materials, the mass could be far higher, explaining the negligible non-gravitational acceleration. If it is less dense, a fluffy aggregate of ice and dust, the lack of trajectory change becomes harder to justify. The velocity at entry was exceptionally high for an object of this scale. Interstellar objects arrive with velocities reflecting their ejection from distant star systems, plus the Sun's motion through the galaxy. 3I Atlas came in fast, faster than models predicted for natural ejecta from typical stellar environments. High velocity implies either ejection from a massive star with strong stellar winds or a trajectory shaped by gravitational assists from unseen bodies in its origin system. Neither explanation is impossible. Both require specific conditions that narrow the parameter space. Think about what that means for the object's origin. If it formed in a distant planetary system and was gravitationally ejected, it likely originated from the outer regions where volatiles condense. The carbon dioxide dominance and low water content fit certain formation scenarios in systems where the protoplanetary disk was unusually cold or carbon-rich. Such systems exist. They are not common, but they exist. The trajectory alignment, the timing, the composition, they could all be explained individually by low-probability natural processes. It is the combination that strains credulity. Joint probability is the key concept here. If 20 independent anomalies each have a probability of 1 in 100, the joint probability that all occur together by chance is 1 in 100 to the 20th power, a number so small it loses physical meaning. But the anomalies are not independent. Composition affects outgassing. Outgassing affects brightness. Brightness affects thermal models. Trajectory affects observation windows. The dependencies reduce the joint improbability. But even accounting for correlations, researchers have calculated odds falling below 10 to the negative 30th in some models. Those are not odds. Those are impossibilities masquerading as statistics. Most scientists default to exotic natural explanations. Interstellar ice formed under conditions unknown in the solar system. Subsurface chemistry driven by cosmic ray bombardment over millions of years in deep space. Structural geometries shaped by processes not yet understood. These are reasonable positions. They preserve Occam's razor. They avoid the explosive implications of the alternative. The alternative has been voiced cautiously, primarily by researchers like Avi Loeb, who have argued that the accumulation of anomalies warrants consideration of a technological origin, not as a conclusion, as a hypothesis worth testing. The scientific method does not exclude possibilities because they are uncomfortable. It tests them. The absence of a propulsion signature, the lack of radio transmissions, the failure to detect artificial geometry, all weigh against a technological explanation. But the absence of evidence is not evidence of absence, and the sheer volume of unexplained data keeps the question alive. Here's the problem with invoking technology. If 3I Atlas were an artifact, it would need to have been launched millions of years ago to traverse interstellar distances at observed velocities. It would need to have survived the radiation environment of deep space without degradation. It would need to be oriented by design or by accident on a trajectory that threaded past multiple planets in our system. The engineering challenges are staggering. The energy requirements dwarf anything human civilization has achieved. It is not impossible. It is improbable to the point of fantasy. Yet natural explanations face their own engineering challenges. A comet composed primarily of carbon dioxide, laced with nickel and cyanide, exhibiting extreme negative polarization, outgassing without trajectory change, maintaining structural integrity through perihelion, producing hexagonal jet symmetry, and arriving on a trajectory aligned with the ecliptic and timed for planetary flybys. That object also strains the boundaries of what nature randomly assembles. Now about the data NASA will release tomorrow. If HiRISE images show a smooth, irregular nucleus consistent with a comet, the mystery contracts but does not vanish. Composition and polarization anomalies remain. If the images show geometric regularity, edges, facets, surface features inconsistent with natural accretion, the mystery explodes into a crisis. If the images are inconclusive, ambiguous, or withheld further, the speculation intensifies. Timing is everything. The briefing is scheduled for November 19th, the day before 3I Atlas makes its closest approach to Earth at roughly 280 million kilometers, 10 times farther than the Mars flyby. Ground-based telescopes will track it, but resolution will be limited. After Earth passage, the object accelerates outward, fading, unreachable. This is the last window for detailed observation. If HiRISE data hold answers, they must be released now. Think about what that means for mission planning. NASA and other space agencies have discussed fast response missions to intercept interstellar objects. Oumuamua passed through the inner solar system in 2017, and by the time scientists recognized its significance, it was already beyond reach. Proposals for standby spacecraft, probes kept ready for rapid launch toward unexpected visitors, have circulated for years, but remain unfunded. 3I Atlas provides more warning. Its trajectory was calculated months in advance, yet no intercept mission launched. The reason is simple. Propulsion technology capable of matching velocities with an object moving at tens of kilometers per second relative to the Sun does not exist in operational form. Chemical rockets lack the delta V. Ion drives lack the thrust. Nuclear thermal propulsion could theoretically achieve the required speeds, but no such system is flight-ready. An intercept mission would take years to design, build, and launch. 3I Atlas will be gone in months. Remote observation is the only tool available, and it comes with frustrating limits. Spectroscopy reveals composition but not structure. Imaging reveals shape but not interior. Radar could provide density and rotation data, but 3I Atlas passed too far from Earth's largest radio telescopes for effective ranging. The Arecibo Observatory, which could have illuminated the object with powerful radar pulses, collapsed in 2020. The remaining facilities lack the combination of power and sensitivity needed. Here's where it gets interesting. If 3I Atlas is natural, it represents a snapshot of interstellar chemistry frozen for millions of years, a sample of materials formed in a distant star system under conditions Earth-based laboratories cannot replicate. The scientific value is immense. Comets in the solar system have been baked and irradiated by the sun for billions of years. Interstellar comets arrive pristine, their compositions unaltered since formation. Understanding 3I Atlas means understanding the diversity of planetary systems across the galaxy. If the object is not natural, the implications cascade in every direction. The existence of another technological civilization, capable of interstellar engineering, rewrites humanity's place in the cosmos. It implies intelligence survived long enough to master energies and timescales humans have barely begun to conceptualize. It implies we are not alone. And more unsettlingly, it implies we are not first. Read between the lines of institutional behavior, NASA does not call special briefings for ordinary comets. The agency issues press releases, updates its websites, and moves on. A dedicated briefing, live-streamed, open to the press, with materials prepared in advance, signals that something in the data demands careful public presentation. Either the findings are scientifically momentous, or they are ambiguous enough to require framing to prevent runaway speculation. The history of interstellar object discoveries is short. Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025, 3 objects in 8 years. Statistical models predicted interstellar visitors should pass through the inner solar system roughly once per year, but most would be too faint to detect. Improved telescope networks, particularly the upcoming Vera C. Rubin Observatory, with its wide-field survey capabilities, are expected to detect dozens per year once fully operational. 3I Atlas may be unusual, but it will not be unique. The question is whether future visitors will show similar anomalies or whether this object represents an outlier. Outliers demand explanation. In a sample size of 3, one outlier is noise. In a sample size of 3, one outlier might be signal. The scientific method requires larger datasets. The universe, indifferent to human timelines, will provide them at its own pace. The cyanide traces are worth revisiting. Hydrogen cyanide is a common interstellar molecule detected in molecular clouds and protoplanetary disks. Its presence in comets is not shocking. The concentration matters. If 3I Atlas carries significantly higher cyanide levels than solar system comets, it suggests formation in an environment rich in carbon and nitrogen, possibly near a star with a different spectral class than the Sun. Cooler stars, M dwarfs, dominate the galaxy numerically and often have protoplanetary disks with different chemical balances. An origin near an M dwarf could explain the composition. The nickel-to-iron ratio is harder to dismiss. Meteorites and asteroids show predictable ratios based on condensation sequences in the solar nebula. High nickel with minimal iron inverts those expectations. It suggests either a formation environment with unusual oxidation states or a differentiation process that separated metals in ways not observed in solar system bodies. Both scenarios are physically plausible. Both require specific, narrow conditions. Here's the problem. Each anomaly, taken alone, has a natural explanation that stretches but does not break physical law. The retrograde trajectory could be random chance. The anti-tail could result from an unusual dust grain size distribution. The composition could reflect an exotic formation environment. The polarization could stem from materials not yet synthesized in terrestrial labs. The lack of non-gravitational acceleration could mean the mass is underestimated. The hexagonal jets could emerge from subsurface fracture patterns. The solar flare correlation could be coincidence, but explaining them all simultaneously requires invoking a sequence of low-probability events, each independent, each rare, all occurring in the same object. At some point, the cumulative improbability exceeds the threshold where natural explanations become less parsimonious than alternative hypotheses. That threshold is subjective. It varies by researcher, by field, by philosophical stance on what constitutes extraordinary claims, requiring extraordinary evidence. Avi Loeb has publicly argued that the threshold is crossed. He points to the joint probability calculations, the lack of satisfactory natural models, and the scientific obligation to investigate all hypotheses. His critics argue that invoking technology without direct evidence, a radio signal, a spectral signature of artificial materials, a detectable propulsion exhaust, is premature and distracts from legitimate research into natural processes. Both positions are defensible. Both shape how the data are interpreted. NASA's briefing tomorrow will likely steer carefully between them, presenting observations without strong conclusions, emphasizing what remains unknown, rather than speculating on what might be. That is the institutional default, and it is scientifically appropriate. But it may not satisfy a public primed by decades of science fiction to expect definitive answers. Stop and consider that the Mars Reconnaissance Orbiter was not designed to image interstellar objects. HiRISE was built to study Martian geology, to map landing sites, to search for water ice and mineral deposits. Its use to observe 3I Atlas is opportunistic, a redirection of resources to capture a fleeting target. The images will not have the resolution to show surface features smaller than tens of kilometers. If the nucleus is 5 kilometers wide, HiRISE might resolve it into a handful of pixels. If it is 20 kilometers wide, more detail emerges, but still nothing close to what would be needed to identify artificial structures unless those structures are conspicuously geometric. Think about what that means for interpretation. Ambiguity will dominate. If the nucleus appears lumpy and irregular, consistent with a comet, that supports natural origins but does not exclude the possibility of a natural shell surrounding something else. If the nucleus appears smooth and geometric, that raises questions but could still result from unusual sublimation patterns, eroding the surface into regular shapes. If the images show nothing useful, smearing from motion, overexposure from brightness, obscuration from the coma, frustration will mount. The ghost shell remains one of the most visually striking features. A detached ring of material expanding outward from the nucleus implies a sudden release of energy. Comets undergo outbursts when subsurface pockets of volatile ice are suddenly exposed and flash into gas, blowing off overlying dust. The force can be significant. The symmetry of 3I Atlas's shell suggests the outburst was unusually uniform, either because the volatile pocket was evenly distributed beneath the surface, or because the triggering event happened simultaneously across the nucleus. Simultaneous triggering is hard to achieve naturally. Solar heating is gradual, asymmetric. Cosmic ray impacts are random. Internal radioactive decay is diffuse. A fracture propagating through the interior could theoretically trigger a symmetric outburst if the nucleus had pre-existing weaknesses arranged in a regular pattern. That returns to the question of structure. Random accretion does not produce regularity. Differentiation, layering, or repeated freeze-thaw cycles might. Here's where things get strange in terms of observational bias. Telescopes have limited time. Observers prioritize targets based on predicted scientific return. 3I Atlas became a priority only after initial observations revealed anomalies. By the time resources were marshaled, the object had already passed key observation windows. Data gaps are inevitable. Some anomalies might be artifacts of incomplete coverage. Brightness spikes could correlate with observation scheduling rather than intrinsic variability. The absence of certain spectral lines could reflect insufficient signal-to-noise in the wavelength searched. But the major anomalies, trajectory, composition, polarization, lack of non-gravitational acceleration, do not hinge on sparse data. They are confirmed by multiple independent observatories using different instruments. The anti-tail was imaged by both ground-based telescopes and space-based platforms. The composition was measured spectroscopically with high confidence. The polarization was replicated across observing runs. These are not artifacts. The trajectory deviations, 4 arcseconds on October 29th, are smaller and more suspect. Astrometry, measuring the position of objects against the background stars, requires precise calibration. Atmospheric turbulence, telescope pointing errors, and reference star catalog inaccuracies all introduce noise. 4 arcseconds is detectable but not definitive. It could be real. It could be measurement error. Distinguishing between them requires more data points, more observations, and statistical analysis that accounts for systematic uncertainties. NASA's Jet Propulsion Laboratory maintains the most authoritative ephemerides for solar system objects, updated continuously as new observations arrive. If 3I Atlas consistently deviates from predicted positions, JPL's models will flag it. If the deviations are random, scatter around the predicted path, they are noise. The briefing may address this, or it may sidestep it as inconclusive. Now about the data architecture. Observations of 3I Atlas are scattered across institutions and databases. Ground-based observatories, space telescopes, amateur astronomers, and classified military sensors all contribute. Integrating that data into a coherent picture requires coordination, standardization, and access. Some observations are proprietary, held by research teams until publication. Some are classified, collected by defense assets tracking near-Earth objects, but not released publicly. The full dataset does not exist in any one place. This fragmentation complicates analysis. Researchers working with partial data may reach conclusions that would be overturned by data they do not have. Duplication of effort wastes time. Contradictory results emerge from different groups analyzing different subsets. NASA's briefing offers an opportunity to synthesize, and NASA's to present a unified picture drawing on all available sources, at least those cleared for public release. What remains classified is an open question. The United States Space Force operates the Space Surveillance Network, a global array of radar and optical sensors designed to track satellites and debris. Those sensors have the sensitivity to detect objects like 3I Atlas. The data they collect are often classified to protect information about sensor capabilities and orbital tracking methods. If Space Force sensors observed anomalies not seen by civilian instruments, that information may not be disclosed. International collaboration adds another layer. Russia, China, and Europe all have space surveillance capabilities. They all observed 3I Atlas. Whether they share findings openly depends on geopolitical considerations and institutional transparency norms. Russia's space agency, Roscosmos, has been less communicative in recent years. China's data-sharing policies are opaque. Europe's ESA is generally open but coordinates with member states that may impose restrictions. The possibility of withheld data fuels conspiracy theories, which are unproductive but inevitable. The challenge for institutions is to balance transparency with the legitimate need to verify findings before public release. Rushing to announce results that later prove erroneous damages credibility. Delaying too long invites speculation that something is being hidden. NASA's 6-week gap between the Mars flyby and the briefing falls into the gray zone, where both explanations, careful verification, and deliberate secrecy remain plausible. Read between the lines of mission design. The Mars Reconnaissance Orbiter, launched in 2005, carries fuel for orbital adjustments until at least 2030 and remains one of NASA's most scientifically productive assets. HiRISE has imaged Martian terrain in exquisite detail, discovering recurring slope lineae, avalanches, and gullies that transformed understanding of Martian surface processes. Redirecting it to image an interstellar object represents a significant operational decision, prioritizing 3I Atlas over Mars science for at least one imaging sequence. That prioritization implies institutional judgment that the object's scientific value outweighs the opportunity cost. Routine comets do not receive such attention. Oumuamua did, briefly, but it passed too quickly for coordinated campaigns. 2I Borisov was observed extensively but showed conventional comet behavior: water-rich composition, predictable brightness, normal polarization. It confirmed that interstellar comets exist and resemble local ones. 3I Atlas does the opposite. Here's where it gets interesting in terms of sample size. If interstellar objects fall into two categories, conventional comets like 2I Borisov and anomalous objects like 3I Atlas, the ratio between them constrains models of how planetary systems eject material. Conventional comets likely originate from systems similar to ours, where water-ice dominates and gravitational interactions with giant planets fling objects into interstellar space. Anomalous objects might come from systems with different chemistries, different architectures, or different formation histories. Alternatively, if most interstellar objects are conventional and 3I Atlas is a rare outlier, it may represent an extreme tale of the natural distribution, an object formed under conditions that occur only once per billion comets. Rare is not impossible. The galaxy has billions of stars, trillions of comets. Sample enough of them, and the 1 in a billion case eventually arrives. Or 3I Atlas is not a comet. It is something else, employing the comet classification as a placeholder because no other category fits. The term interstellar object is deliberately neutral, avoiding assumptions about composition or origin. But language shapes thought. Calling it a comet primes scientists to look for comet-like explanations. Calling it an object leaves the door open. Think about what that means for public communication. The briefing's language will be scrutinized. If NASA refers to 3I Atlas as a comet, it signals confidence in a natural origin. If they use object or visitor, it implies uncertainty. If they introduce qualifiers, unusual comet, anomalous object, it acknowledges the data do not fit neatly. The choice of words is not accidental. Press questions will push for clarity. Reporters will ask if the object could be artificial. NASA's response will likely be cautious. No evidence supports that hypothesis, but all possibilities are being considered. Further observations are needed. That is the scientifically correct answer. It is also the answer that fuels speculation because it refuses to rule anything out. Public interest in interstellar objects has surged since Oumuamua. The name itself, Hawaiian for scout or messenger, carried romantic overtones that captured imaginations. Loeb's subsequent book arguing for a technological origin became a bestseller, debated widely, and polarized the scientific community. Some researchers welcomed the attention, seeing it as an opportunity to engage the public with cutting-edge science. Others resented the sensationalism, arguing it distorted the careful, incremental process of hypothesis testing that characterizes real research. 3I Atlas arrives into that charged environment. The anomalies are more numerous and more pronounced than Oumuamua's. The data are richer. The stakes feel higher. If this object proves to be natural, it is still a scientific treasure. If it proves to be something else, it is the most important discovery in human history. Stop and consider that no discovery of that magnitude happens cleanly. There will be false starts, retracted papers, bitter disputes over interpretation. The data will be messy, observations will conflict, models will fail to converge. The process will be frustrating, public, and protracted. Science does not deliver neat answers on convenient timelines. The upcoming close approach to Earth on November 20th offers one final intensive observation window. Ground-based telescopes across the globe will track 3I Atlas, collecting photometry, spectra, and polarimetry. The combined dataset will be larger than anything available for previous interstellar objects, but the object will be farther away than during the Mars flyby, limiting resolution. The trade-off is unavoidable. What comes next depends on what the data show. If the briefing reveals something definitive, clear images of the nucleus, resolved structure, anomalous features, the scientific community will mobilize. Papers will be drafted, peer review will be fast-tracked, follow-up observations will be scheduled. If the briefing reveals ambiguity, the debate will intensify. Researchers will argue over statistical significance, systematic errors, and alternative models. Progress will be slow. Instruments under development offer hope for better data in the future. The Vera C. Rubin Observatory, scheduled for full operations in 2025, will survey the entire visible sky every few nights, detecting faint, fast-moving objects that current telescopes miss. It will catch interstellar visitors earlier in their approach, providing more time to coordinate observations and potentially intercept missions. The James Webb Space Telescope, already operational, has the sensitivity to observe faint objects in infrared wavelengths where thermal emission dominates. If another interstellar visitor approaches, JWST could characterize its temperature, composition, and outgassing in unprecedented detail. But JWST's field of view is narrow, and its observing time is fiercely competed for. Securing time to observe a transient target like an interstellar object requires convincing a review panel that the science justifies displacing other planned observations. NASA's proposed Comet Interceptor mission, a spacecraft designed to wait in space until a suitable target appears, would launch to intercept a long-period comet or interstellar object. The mission is still in the planning phase, with launch no earlier than 2029. If it flies, and if another interstellar visitor arrives on a favorable trajectory, humanity might finally obtain close-up images and direct composition measurements from an object born in another star system. Here's the problem with waiting. Interstellar objects move fast. By the time they are detected, weeks or months of lead time are available at best. Designing, building, and launching a spacecraft in that window is impossible with current technology. Comet Interceptor pre-positions the spacecraft, waiting in a gravitationally stable orbit until a target appears, then racing to intercept. The concept is sound. The engineering is challenging. The timeline is uncertain. 3I Atlas will not wait. It will make its closest approach to Earth, fade into the distance, and vanish from human view within months. The data collected now are the only data that will exist. No second chances. No do-overs. Think about what that means for the historical record. 50 years from now, scientists will look back at the observations of 3I Atlas and judge whether the right measurements were made, whether the right questions were asked, whether the opportunity was used wisely. Those future scientists will have better instruments, better models, and more interstellar objects to compare. But they will not have this object. The window is closing. If HiRISE images show geometric features, straight edges, right angles, repeating patterns. The reaction will be immediate and seismic. Peer review will be bypassed by press coverage. Social media will explode. Governments will demand answers. The scientific community will fracture into factions debating interpretation, authenticity, and implications. The process will be chaotic. If HiRISE images show a mundane, irregular nucleus, the anomalies do not disappear. Composition, polarization, trajectory, and outgassing behavior still demand explanation. Natural models will be refined. New formation scenarios will be proposed. The object will remain scientifically important, but culturally less explosive. If HiRISE images are inconclusive, blurred, ambiguous, or withheld, the frustration will be intense. Speculation will run unchecked. Trust in institutions will erode among those predisposed to skepticism. The scientific method relies on transparency and reproducibility. Withheld data, even for legitimate reasons, undermines that foundation. Now about the data on radio frequency emissions. The 1665 to 1667 MHz absorption lines correspond to hydroxyl radicals, the OH molecule formed when water breaks apart under ultraviolet radiation. Comets emit at these frequencies because the sun's UV light constantly dissociates water molecules in the coma, creating a cloud of OH radicals. Detection of emission is routine. Detection of absorption is not. Absorption means the object is positioned between the observer and a background radio source, with the OH radicals blocking specific wavelengths. For that geometry to occur, the comet must be transiting a bright radio source, a quasar, a distant galaxy, or another celestial radio emitter. The probability of such an alignment is low, but not impossible. It depends on the density of background radio sources along the comet's path and the angular size of the comet's coma. Alternatively, yesimai voltrine, yestiale the absorption could indicate something about the internal structure or density distribution of the coma, with self-absorption occurring as radio waves from the nucleus or inner coma pass through the outer coma. That would be unusual but not unprecedented in dense cometary environments. The radio data are sparse. Few observatories were monitoring 3I Atlas at radio frequencies during the relevant observation windows. More data would clarify whether the absorption is an artifact, a geometric coincidence, or an intrinsic property of the object. Those data do not yet exist. Here's where it gets interesting with the solar flare correlation. The sun's magnetic field is complex, driven by internal dynamo processes that are not fully understood. Flares result from magnetic reconnection events, where twisted field lines suddenly snap and release energy. Predicting flares remains an inexact science. Clusters of flares occur, sometimes separated by quiet periods, following patterns that appear random but likely reflect underlying dynamics not yet captured in models. The quiet period leading up to 3I Atlas's perihelion, followed by a sudden burst of X-class flares immediately after, fits within the range of natural solar variability. It could be coincidence. Solar physicists note that the current solar cycle, cycle 25, is more active than initially predicted, and flare clustering is expected during the rise towards solar maximum. But the timing is precise enough to warrant scrutiny. If subsequent analysis shows that the flares originated from regions of the solar surface facing the comet at perihelion, a causal link becomes harder to dismiss. If the flares originated from regions on the opposite side of the sun, correlation without causation is the simpler explanation. Read between the lines of institutional caution, claiming a connection between a comet and solar flares without robust evidence invites ridicule. The energy scales are mismatched by orders of magnitude. The sun dwarfs the comet, yet magnetic phenomena are subtle. Small perturbations can trigger large events if conditions are poised near a critical threshold. A comet's ionized coma, interacting with the sun's magnetic field, could theoretically introduce a perturbation. Whether that perturbation is large enough to matter is a question for magnetohydrodynamic simulations, which have not been run for this scenario. The broader question is what science does with improbable correlations. Dismiss them as noise, and potentially meaningful signals are lost. Investigate everyone, and resources are wasted chasing phantoms. The balance is delicate and subjective. 3i Atlas will be studied for years. Papers will be published. Conferences will dedicate sessions to it. Models will be proposed, tested, and refined. The scientific process will grind forward, indifferent to public impatience. But the briefing tomorrow is the moment when institutional authority weighs in, when NASA, the agency that put humans on the moon, that explores Mars, that peers into the deepest reaches of space, tells the world what it knows and what it does not. If the briefing is anticlimactic, interest will fade. Researchers will continue their work, but the public will move on. If the briefing drops a revelation, the world changes. There is no middle ground in terms of cultural impact. Stop and consider that the universe does not owe humanity clarity. The data are what they are. Nature is under no obligation to make sense on human timescales or within human frameworks. If 3i Atlas remains unexplained, that is the reality. Science progresses by accepting uncertainty, refining models, and waiting for more data. But the human mind craves resolution. Ambiguity is uncomfortable. Mysteries demand solutions. The tension between scientific patience and human urgency will define the public conversation around 3i Atlas for as long as the object remains in the spotlight. Think about what that means for the next interstellar visitor. The lessons learned from 3i Atlas, what instruments to use, what measurements to prioritize, what coordination is needed, will shape the response. If detection networks improve, if mission concepts mature, if international cooperation strengthens, the next object might yield answers. This one does not. Or the next object will bring its own mysteries, deepening the enigma rather than resolving it. The final question is simple and terrifying. If the data from HiRISE, from spectroscopy, from polarimetry, from radio observations, from trajectory analysis, if all of it, integrated and verified, points towards something that does not fit natural models, something that demands consideration of alternatives our scientific frameworks barely accommodate, then what? How does the world react to confirmation that intelligence, technology, engineering, that minds other than human, have reached across the interstellar void? How do institutions, governments, religions, philosophies adjust to the reality that the universe is not silent, that the Fermi paradox has an answer, and that the answer is here, now, imaged by a camera orbiting Mars? The briefing is tomorrow. The data are either already in hand, sitting in encrypted files, reviewed by a small circle of researchers bound by non-disclosure, or they are being finalized, formatted, prepared for presentation. Either way, the countdown is measured in hours. 3i Atlas does not care. It moves according to gravity and momentum, indifferent to the questions it raises, the debates it ignites, the implications it carries. It entered the solar system from the darkness between stars, past the sun, and now accelerates back toward that darkness, leaving behind a trail of data points and uncertainties. If tomorrow's briefing reveals nothing conclusive, the anomalies persist. 20 contradictions, each individually explainable, collectively implausible. A trajectory aligned with the ecliptic at 1 in 500 odds, timing for planetary flybys at 1 in 20,000 or worse. Composition unlike any solar system body. Polarization never before recorded. Outgassing without trajectory change. Hexagonal jet symmetry, a ghost shell. Solar flare correlation. Absorption instead of emission at radio frequencies. Survival through perihelion without fragmentation. And HiRISE images, withheld for 6 weeks, about to be revealed. If the images show structure, repeating geometry, edges, facets, if they show anything that cannot be dismissed as natural erosion or random accretion, then the mystery does not deepen. It shatters. Because at that point, the question is not what 3i Atlas is. The question is, who sent it and why?